bury the waste in your backyard.
Yeah, but California is closing down its last nuclear plant because nuclear bad. They are pursuing a lot of policies emotionally, but not rationally. It's kind of it's kind of scary, sad. Oh, that's pretty.
Yeah, I could watch this a lot.
I saw one this week somewhere. I think NASA released it. It showed 2 diagrams. It showed what the Earth looks like from the moon and what the moon looks like from the Earth. And then a little inset showed the orbital position, because the phase of the moon is always opposite the phase of the Earth. If you were standing on the moon, whatever phase the moon is in, the Earth would be in exactly the opposite phase.
Just a flip. Okay.
Yeah, it's always opposite. So if you're on the near side of the Earth where you can see the moon is always brightest. The Earth is always brightest at midnight. So there you go. Sounds like a title for a new science fiction book.
Yeah, that's right. That's right. There's some sort of romance movie or something.
Yeah.
Yeah.
Romance movie. No, I'm working on a new sci-fi. I've published a number of them, but I'm working on a new one. And I decided I would like to try a hard-boiled detective thriller set on Mars.
Noir, huh?
Yeah, no, noir. Yeah, exactly. A detective noir set on Mars. And thinking a lot about what a frontier society would look like in the 22nd century. So.
So do we send, once we can send large groups of people, do we send our best and brightest, or do we send?
Initially, it will be.
What happens after that?
Well, at some point, I think one of the issues will be that transporting large machinery will be ridiculous. Establishing, bootstrapping an industrial base to produce large machinery will be ridiculous. And so for the first time since perhaps the 17th century, human labor in transportation, indentured servitude as labor, will become an economically viable model. I also don't believe for a hot minute that governments will be able to colonize Mars. It will be corporations and industrial concerns that will colonize Mars. And in my future scenario, we don't have governments. We have dome ecologies with basically local corporation. And if you want police protection or investigation, or if you want justice basically for a crime that's been done, if you're not within a corporate structure where the corporation polices itself, then you go hire it done. Justice is for hire, quite literally. And so that's some of the basis.
Sounds expensive.
Yeah, there would be on the frontier people who can't afford, it's kind of a jungle law, but since all life and all labor are precious, the idea of free-for-all crime and murder is really highly disapproved of. And if you kill somebody, you're likely to get, just mob lynched rather than brought in for trial, because you're taking labor away. And in a market where labor is a very precious commodity, because industrial capacity is very poor, it becomes interesting.
Well, maybe we have AI beings up there that kind of keep the peace. Who knows?
I hope not. Yeah, I've read too much Asimov to be content with it.
Yes, you have.
Watching Apollo footage of astronauts doing geology on the surface of the moon is a really great way to think about preparing for Artemis, for putting people on the lunar surface once again. We learn a lot in how they did science operations on the moon and what it's like to work on the moon. You see them doing geology. You see them taking rock samples, putting in a drive tube to take a core sample. You see them bouncing along the surface of the moon on the lunar rover that they used in Apollo 15 through 17. So it's a great way to help drive technology development for the next generation of spacesuits and geology sampling tools.
There's these facilities that help us train like we are on the lunar surface. You know, these 1,6G offload systems or putting people in the aquatic environment are great ways to train the mobility part, right? Like, what can you do and how different does it feel to be in 1,6G and do these tasks?
We've been training astronauts in geology and geoscience for decades now. The Apollo astronauts had literally hundreds of hours of training in geology before they flew to the moon. It's often said that the Apollo astronauts had the equivalent of a master's degree in geology by the time they flew to the moon. In the intervening decades since Apollo, we've been training astronauts who fly to the International Space Station because when they're on the ISS, they spend time observing the Earth, looking out the window, taking pictures of what they see on the Earth's surface. Now that we're looking at putting astronauts on the surface of the moon, we also take them into the field. We take them to field sites here on Earth that resemble field sites that we expect them to see on the moon.
That's the reason why we take them out into places that are unique, like volcanic landscapes or places that are analogous to the lunar surface, to train them on the scale and fidelity of science that you just can't recreate in these facilities.
And so by combining this classroom and field training, we're able to prep them for fundamentals of geology, the major driving lunar science questions that we have that we hope to address with the Artemis program, and teaching them how to do field work in relevant analog environments.
For just science aspects of developing new spacesuits, can it get you to where you need to go? And then once you get there, can you do the cool science that you need to do? And so that's, can you move effectively and efficiently in the suit to be able to collect the samples or use the tools or the instruments? For the visibility, it's like, can you make the necessary observations that you need to? Or does the suit have the lights on it that it needs to illuminate the surface and make the observations you need to? The lunar South Pole holds tremendous resources that are going to allow us to continue to explore. This is a place that we've never been before. There's so much to be learned from getting boots on the ground and exploring a unique place that challenges us as humans and also helps us develop technologies that make our everyday life that much better.
We think there might be volatiles present at the South Pole. By using these volatiles, we'll be able to do things like create drinking water, create rocket fuel to launch astronauts back to Earth. And so by harnessing the power of the land, we'll be able to help astronauts establish that long-term sustainable presence.
It's human nature to explore. Pushing our boundaries and exploring our universe is, I think, just one of those things that's just stuck in our human nature, and that we need to do it in order to understand the world around us, including our Earth and our solar system.
Well, hello everybody. Happy Monday. Hope you guys had a great weekend. It was relaxing, and here in Arkansas it was typical 4th of July weather, which was nice. It was clear enough to see fireworks, and and everybody was out enjoying the day, doing barbecue, ice creams, you name it. So all the classic Americana 4th of July things are happening here. So you should, if you get a chance and haven't experienced Heart of America 4th of July celebrations, Northwest Arkansas is a pretty cool place to do it at. So anyhow, this is episode 16 of Dr. Barth's How Do You Know series, and he's come all the way down to the origin of the moon. So, and it's not as simple of a story as you might think, right? And I guess the adventure continues on. So,
It does.
Daniel, I'll turn it over to you.
Thank you. Thank you, Scott. This is our fifth program in the Dynamic Moon series. This is our fifth and final program. And I love the opening, but I must tell you, Scott and I were discussing colonization and other issues. And I mentioned that I thought that colonization of Mars would be done by corporations rather than governments. Taking nothing away from the folks at NASA who are brilliant and awesome, but I think it's absolutely damning that that little video starts off with saying, we can learn a lot by watching the videos of people doing geology on the moon. The reason we're watching videos, of course, is we've waited 6 decades, and those people who planned those missions, ran those missions, are mostly gone now, or they're very, very elderly. And so we're reinventing the wheel. And this is just, this administration says, I'm not going to support what that administration supported, and the political football nature of space exploration, which is why I think that governments won't be doing colonization. But that's just a little sidelight. When we go back and we look at these things we've talked about with moons, we've talked about tides, we've talked about the Roche effect, we've talked about the idea that you can't put a moon anywhere you want. We've talked about the idea that all moons are doomed, no moons are permanent, and that moons transition either to become asteroids or they become rings. And we finally come around full circle now. How did the moon get here? What is the story of the origin of the moon? I'm really glad that I'm the age I am, that I had the opportunity to see the things I did firsthand and live through them. The whole origin story for the moon is radically different now than it was when I was in school. And it was one of these lovely things where in the early years of the Apollo program, the early years of NASA, we talked about going to the moon, and two of the major goals, and people forget this, two of the major goals: one, to actually find out how far away from the sun we are. Very difficult, if not impossible, to do that with only measurements from the surface of the Earth. So the idea of measuring the AU was done for the first time on the Apollo 11 mission, where it was first done accurately from 2 different points. You had a decent baseline. The second thing people wanted to find out is, how did the moon get here? We've talked about, well, the moon has been permanent as far as human history is concerned, but that's not really permanent in astronomical terms. But nevertheless, the moon has always been with us as a civilization, as a people, as a species. And we get these ideas of, gee, where did the moon come from? And this is an interesting idea. Of course, every civilization has these cosmic origin stories. How did we get here? How were we created? How did the universe form? How did the moon form? It's one of these sets of cultural, and there are as many stories as there are civilizations. Many of these traditions are oral history that passed down. Some of them have been written down, but I would imagine there are more that have not been written than have been written. Nevertheless, one of the things I want to stress to you, and again, we go back so many times in this program series to the major pathfinders of astronomy, and Galileo was one, and Galileo famously warned Pope Urban VIII, and he said, do not make tenets of science into political or spiritual doctrine, because science always changes. My blood boils every time I hear some knucklehead say something like, the science is settled, or do you believe in X, Y, or Z?
Scientific fact.
That's right. The science is settled, and this is no longer a theory. And I'm like, you know what? I don't know if you're trolling for stupid or if you're just proudly proclaiming your ignorance of how science works, but the science is never settled. And this is kind of a lesson in that. I teach my students in every science class I have, and one of the first things I tell them, we do not engage in science to prove we are right. we engage in the activity of science to become more right. We follow the facts humbly where they lead. And we see all too often science becomes politicized. One theory becomes, and this isn't the 21st century. This isn't the modern Democrat Republican Party issue. This has been going on for millennia, where certain scientists and proponents of theories become the darlings of administrations and regimes. And this has been going on for millennia, and not just in Western civilization, but in all civilizations. And inevitably, when we get someone who is ostensibly a person of science who answers to political masters or economic masters, I mean, it doesn't matter if your master is a political party or a corporation, bent on making cash out of your cleverness. Basically, we get into this trap where we put our hand in the coconut and we can't pull it back out again. And it's as Sherlock Holmes says, it's a capital mistake to theorize in advance of our data, because insensibly one begins to twist facts to fit theories instead of twisting theories to fit facts. Conan Doyle, in the persona of Holmes, understood that theories are malleable, facts are not. Now, we may discover we were mistaken. The neutrino doesn't weigh as much as we thought. The proton is this big, or there are actually quarks inside of neutrons. We may discover that we were mistaken or ill-informed, but we cannot just go and twist facts to fit our pet theory. We end up spouting nonsense. The latest nonsense that I've seen, and I follow these things, Scott, because I'm interested in science and education. And I have people tell me all the time, oh my gosh, you teach science? That's so hard. No, it's not. If you think that's hard, look at some of the conspiracy theories and realize that you've not only you've taught people this and then convinced them you're right. The latest one I came across this weekend, because I troll through the soft mushy bottom of the internet sea where it's mud and decay. The latest one I came across is birds are not real. And there's actually somebody who came out in 2017 and said, starting with the Kennedy administration, that what they did is they started slaughtering all the avians and replacing them with drones so they could effectively surveil all the population on the world. I'm like, it would take a marvelous superhuman industrial base that we haven't got to do this. But of course, rationality has nothing to do with it. People come up with these crazy ideas. They had a rally in Springfield, Missouri in support of this crazy conspiracy theory. If you can teach people that, certainly teaching people things like the origin of the moon or how far it is to Proxima Centauri or how telescopes work, there's got to be a piece of cake, because you can actually show people with real activities and experiments, this is how it works. But we come back to the idea of twisting facts to fit theories. Before Apollo, there were three primary theories of the moon's origin. And it's one of these theories my sons really enjoyed, because they all have kind of the same sort of twisted sense of humor as Dad does. There were three major theories on where the moon came from before Apollo, and none of them were right. They were all wrong. And these theories that were in the books, they were in my textbooks as a child. Do you remember fission theory, Scott? The idea that the Earth spun really fast and the moon tore off. And
right.
One thing.
Yeah, when we were kids, they would show this kind of.
Yeah, that was in the textbooks.
Yeah.
That was in the textbook. So we're going to go over these theories, and we're going to say, gee, here's the theories, and here's what people advocated and said, I think this is right. And here's what they said they were going to look for if Apollo got evidence to support them. And here are the problems with the theories going forward that maybe you should have said, well, it doesn't look realistic, but let's go ahead and just follow the story where it leads. So we're going to talk about the fission theory. And once again here, I'm going to show some pictures and share my screen with folks. And so here we are. This is a diagram that I saw in my textbooks as a boy.
Yep.
Did you see this one, Scott?
Yep.
Yeah, this was kind of the leading one. The idea that, oh, at one time you had this molten Earth, kind of like, I forget what the name of the planet is in Star Wars, where it's all volcanoes. It's kind of like Io, right? It's all volcanic. Right. And at one point it was spinning and spinning and spinning, and a blob ripped off. And if you rip off a blob, you lose angular momentum, and that allowed the rest of it to slow down. And then, hooray. Well, you take a look at this and you go, oh, okay. So what does fission theory mean? Well, something splitting into two parts. Now, we have biological fission, where a cell divides into two copies of itself, and then they grow back to adult size. That's getting 2 out of 1 is generally fission. And of course, atomic scientists have fission. We use fission for nuclear power, uranium and plutonium. The nucleus is unstable, it breaks apart, it releases heat and energy. And so you get this, this fission, which can be used in biology and atomic science, and it's a real thing. They said, oh, so why not planets? Well, when you talk about fission, you get this idea, and I know we're going to get some people, we're going to poke some people.
No.
You get centripetal and centrifugal forces. And I've heard many times, oh, centrifugal force doesn't exist. Well, it's nonsense. That's nonsense. Here, watch. I have a weight and I'm spinning it around on a string, and I'm hoping my knot holds and I don't clobber myself here. But if you think about this, as this is whirling, how does it maintain a circular path? There's an inward pulling force. This is the action, if you will, and you're supplying that force along the string. The Earth does this with gravitation, holds the moon in orbit. Every planet holds its moon. Every star holds its planets in orbits the same way, with a centripetal or center-seeking force. But Newton said for every action, there's an equal and opposite reaction. And so if I have a centripetal force, I'm pulling inward on the string. Guess what? If we construct Newton's laws in a rotational frame, the mass also, there's a reaction force pulling outward. That's the centrifugal force. Center fleeing. So if we think about this and we think, oh, well, the fission theory is pretty reasonable. The centripetal force of gravity just wasn't strong enough. The centrifugal force was too great, and this blob of moon. And so we have this planet, and it's spinning too fast. And boom, here we go. We've torn a hunk out. And it's an interesting idea. And it makes sense because if we take a look at things, we see that things actually do fly apart. And I've got a cool photograph here. And friends, if you download the curriculum guide, the episode guide today that's on the explorescientific.com website, you will find in the footnotes of the curriculum guide, of the episode guide, there's a link to a video where these crazy guys, the slow-mo guys, if you're a YouTube fan, you may know the slow-mo guys. They film all sorts of crazy stuff in slow motion. And what they did is they took a high-speed motor and they attached a CD, and they estimated that the CD would fly apart at around 30,000 RPM, and they just spun it up, and eventually here's the high-speed photograph where eventually the centrifugal forces are too great and the object flies apart. The interesting thing about this, Scott, is you don't see 2 pieces.
Many pieces.
Many pieces. This is what's kind of known as the cake mixer problem for fission theory. If you imagine, and many of us have done this, you have an electric mixer, cake or brownies or cupcakes or whatever. And if you've ever had a youngster in the kitchen, can I help? Can I help make cake? Can I do the mixer a little bit? Sure, okay. And then they pull the cake mixer out of the batter without turning off the motor.
Oh yeah.
You don't get 2 blobs of cake mix around
No.
the kitchen. You get this explosion of cake mix, and the whole thing just sort of detonates. And at that point, you're like, wow, bad day. Yeah, so the other fundamental problem with this theory, if the original Earth was spinning that rapidly that big pieces would tear off, how did it ever coalesce to begin with? Clouds of material that are spinning too rapidly never coalesce into a single solid body. They can't do it. So if it formed at low speed, then how did you spin it up? And we now know about the Yorp effect, and a bunch of very long, complicated names. But basically, the idea that sunlight hitting on one side of an asteroid will cause it to spin. We've all seen these little globes, haven't you? I used to have one.
Yeah. It looked like a light bulb.
It looks like a light bulb with the little black and white veins, and you put it in the light.
White on one side, black on the other, or something.
Right, and the photonic pressure spins it up. It's basically a light sail. Asteroids do spin up, but sunlight is a really inefficient motor. It's really inefficient, and for a body as large as the Earth, no, it's not a functional idea. And under no circumstance could we imagine a solar flux so great that it would spin something up to where it popped apart, especially considering that stars are dimmer and less powerful when they're young than when they're old. So there were some problems, but let's ignore, let's play see no evil on the problems. People often do that with theories. Oh, we'll solve that later, right? Oh, I know that's an issue, but that's on the back burner. We'll solve that later. So what kind of evidence were they looking at? Well, if you had the Earth and Moon created at one time and then they split apart, then obviously they both should be the same age, should they not, since they're pieces of the same thing?
Yep.
Second, the mineral and isotope ratios, at least with the crust, should be
similar,
pretty much identical. I mean, you might say, well, the Moon would be like just a chunk of crust. It wouldn't have any of the core in it because the outer piece spun away. And there was a theory. There was advocates of the theory at one time, and I'm going to share this because this is wonderful. And this is still around, and people still. There was this idea that the Pacific Ocean basin was the site of the fracture where the Moon was torn away.
Right.
And if you take a look at the volume of the Pacific Ocean basin and the volume of the sphere of the Moon, they're close enough if you're being fudgy with your numbers. And people actually said, and I saw this picture in textbooks too. I was surprised I was able to find it on the internet somewhere. And people believed, yeah, it ripped away. And of course, people say, oh, but what about continental drift? Do you realize although continental drift was proposed by Wegener in 1930, it wasn't really accepted as a theory until the 1960s. I was taught as a child, I brought that up because I was always reading stuff. I had a science teacher in 5th or 6th grade. That's not possible. Continents can't move. And the guy brought up an interesting point. He says, well, what force would be great enough to move an entire continent without ripping it to pieces? And, well, how could you move a battleship without ripping it to pieces? Well, you float it in the water. And the continents are afloat on a sea of magma in the mantle. But I wasn't sophisticated enough to defeat that argument as a precocious little youngster. But there were people who actually said, yes, the fission theory is true, and evidence of this is the Pacific Ocean basin. These people also claimed that ripping away the Moon, creating the Pacific Ocean basin, also explained the ring of fire of volcanoes around the Pacific Rim. And so they said, oh yes, this is evidence. And it gives us a very interesting cautionary tale about how we interpret evidence and twisting facts to fit theories. So we had these problems. And so there were a group of other people who said, no, the fission theory doesn't work. Co-formation theory is where it was at. This was also in my textbooks as a child. Well, some scientists believe, and of course we know belief doesn't matter in science, doesn't make a difference. Neither do polls. Co-formation theory was the idea that you had one cloud of gas and dust, and somehow two things formed from it at one time. Now, we have a lot more data now than people had in the 1950s and early 60s. And we have actually photographed young star systems where a star is being born. It's very young, a few million years old. There's a dusty disk, and we actually show gaps in the disk where planets are forming. And we've photographed these things. Hubble has photographed these things.
Mm-hmm.
And so we look at this and we say, well, we know that things form in their own orbit, but we've never seen an incidence where one cloud of material has formed separate objects, with the exception of star-forming molecular clouds. Places like the Orion Nebula, stars tend, as the whole thing, and we're talking a massive cloud, many light years wide, collapses and condenses, stars formed and they're gravitationally kicked out. And we're seeing that happen in the Orion Nebula right now. Excuse me. So we see this idea that we could form, and people said, well, if this is true, here's the evidence we expect from Apollo. Again, they said the Earth and Moon should be of identical ages. They should be the same age. And, if they're co-formed, likewise, the Moon should have a core similar to the Earth's core. Because if they both came from, they should both have ostensibly the same ratio. How would you, in one cloud of gas, sort out the minerals to one side and the metals to the other? No mechanism for that. And, but the problem, no one could come up with a mechanism that said from one cloud of gas, two objects with a ratio of 100 to 1 in mass. The idea of one cloud and two equal objects condensing, but the idea of something so unequal as Earth and Moon. And we often do these activities where we say, here's the Earth and Moon. And yeah, the Moon is about 1/4 the size of the Earth, which is true. And this is a lovely 50 millimeter glass marble. You can get these on Amazon. They're brilliant. And this is a classic 20 millimeter marble. So they're about a 4-to-1 ratio, almost perfectly. And yeah, but Earth and Moon, the Moon weighs about 1% of what the Earth does, a little more. But no mechanism for sorting this out in a cloud. How do you get 99% of the material here and 1.5% of the material there? Nobody could come up with a viable mechanism for that. The other interesting thing, if it's co-formed, they should ostensibly have the same density. The Moon's only about 60% as dense as the Earth, about 3.5 grams per cubic centimeter. Earth is about 5.5 grams per cubic centimeter. And this is average for the whole body. We're not talking cores and layers and other things here. And we do see density gradients. Planets, our solar system, get less dense as they move away from the sun. The Jovian moons get less dense as they move out. And we think that has something to do with the temperature at which things condense. And there are mechanisms for that, but nobody could come up with this, we're going to get 100-to-1 mass ratio and a 3-to-5 density ratio. Nobody could come up with that. And so there were groups of clever people who said, well, you know what? A or B, true or false, you're both wrong. And our answer is the capture theory. And their answer, we talked last time about how we classify a moon as something captured and contained within the gravitational well of a planet. And they basically said, the moon was a separate thing. and flew in, and it just got captured by Earth's gravitational pull. Now, at that time, we did not know. Today, we do. The big planets, Jupiter, Saturn, although we don't have a real great confirmation, almost certainly Uranus and Neptune, they capture asteroids all the time. Jupiter and Saturn, particularly Jupiter's right near the asteroid belt. I facetiously described Jupiter and its moons like a 3-year-old with Happy Meal toys. They're always, I want a new one. I've lost my old one. Here, this one's broken. They shred moons into rings. They capture asteroids and collect new ones. Other ones get spun out and lost. Well, there is a mass ratio if you're talking about capture. And again, it's hard to imagine. For those of us that everybody has a smartphone today. If you go to a classroom of 4th graders, how many people have a phone? Most of the children won't. They have no idea how much computing power they actually hold in the palm of their hand. I do. You do, Scott, I'm sure.
Mm-hmm.
I was fascinated with computers as a child. I had an Apple II. I worked with Radio Shack TRS-80s. I worked with the Texas TI-99, the Commodore 64s, where the Apple II, you got BASIC was included. It was built in, hardwired into the machine, and you got a book. Here's how you program your computer. It didn't come with software.
No operating system.
Yeah, you didn't have an operating system. You could buy an operating system, but it was hardwired in. The operating system they had wired in, it would allow you to store data on a cassette tape.
Okay.
And you had an RF radio frequency connection to broadcast the signal to your television. It didn't come with a monitor either. And so you would program things. Oh, look, I've made this software. There was no internet. There was no exchange. They had bulletin board sites. Remember bulletin board sites with
Sure do. Yeah.
14.4 modems, and you would upload your thing, and you could download things, and you heard the screechy.
Slower than 14.4.
Oh yeah. 4K modems were a thing.
Yeah.
And at one point, 4K. I have a 4K modem. Yeah. The Apple II, people forget. It was sold with 16K of memory. That's not meg, kids. That's K. 16,000 byte memory. And it operated at 0.5 megahertz. Not gig, 0.5 megahertz. Things today are literally millions of times more powerful. So you think about this, and they said, well, capture theory. There was no software computer system capable, not even a programming language sophisticated enough to actually do simulations of how big a thing could you actually capture. And so the interesting thing about the evidence, though, is they said, well, if the moon is captured, it doesn't have to be anything like the Earth. We expect it to be a different age, a different composition in terms of metals and minerals. Isotope ratios are going to be all different. It might even not be from this solar system. It might be extra solar. And so the moon should be completely different. Now, today, computer simulations indicate that if you're going to capture something, that a couple of things happen. First of all, if your mass ratio is greater than 10,000 to 1, you're probably too big to be captured. Because what it amounts to, Scott, it's an energy problem. Something is coming along with orbital energy, and it has to lose enough energy to enter orbit. We encountered this problem when we sent the Messenger probe to Mercury.
Okay.
How do we put something in orbit around Mercury? Essentially, you think about it, how do you fall that far towards the sun and then put the brakes on and stop? Right? So whenever you go into orbit, they either do aerobraking. The Mars Curiosity rover used aerobraking in rockets, fly through the atmosphere of Mars. The other thing, if you go deep into the NASA stuff, when you see probes going to different planets, they go and they lose energy And then they have this highly elliptical orbit, and they take sometimes months, even a year or more, to get their orbit to circularize. Things that are captured tend to come in, and they are captured in this highly elliptical orbit that gradually becomes more circular. And the other thing is captured objects can come in from anywhere on the ecliptic. And in other words, their angle of orbit, their orbital angle relative to the plane of the ecliptic can be anywhere for a captured object. Well, we look at the moon and we see that the moon's orbit is very close to circular, so close to circular that it was the 17th century before Kepler actually proved it was an ellipse and not a circle, right? The moon's orbit is aligned within 5.5 degrees of the ecliptic, so it's not wildly tilted. So these two things kind of tended to indicate against capture theory, but again, we didn't have the simulations to say, oh, look, we've run it on the computer and we should see this. We didn't have that data. And so we have these three lovely theories. We have fission, we have co-formation, we have capture, and then the Apollo astronauts come back and say, the answer to the riddle is all y'all are wrong. And it's kind of interesting because when I looked back and I tried to find data on all of these, which were current things when I was young, fission theory you can find. Co-formation theory, you cannot even find a graphic to illustrate it. Same way with capture theory, you can't find many references to it on the web. It was so thoroughly discredited that you can't find evidence for it on the web anymore. It's kind of interesting. Things that have been lost to our history. So Apollo comes back, and Apollo had some interesting data. First of all, they said the moon is significantly younger than the moon. Oh, the Earth comes out as 4.5 billion years, and the moon is 4.4 billion years, which doesn't sound like much, but it's 1 to 200 million years younger. That's not a little bit. If they were dating, it would be creepy because 200 million years younger is just a lot. The next thing they found was, yes, they're not the same age. Second, the moon looks very much like the Earth's crust, but not like the Earth in toto. And so, oh, the moon is like the crust of the Earth. This looked like, oh, the fission theory might be true. They found that the moon is deficient in heavy metals. The nickel, iron type metals, almost totally absent on the moon. Heavier precious metals, no one's found any. So the moon is made up of aluminum, magnesium, and sulfur, some phosphorus, but your heavy metals just aren't there. The other interesting thing, remember they planted seismometers on the moon, right? For moonquakes. Just like on Earth, seismic waves passing through the interior give you a picture of what's going on inside the planet. The moon's core has a diameter of about 480 kilometers. It's about 14% of the moon's diameter. The Earth's core is 7,000 kilometers wide. It's about 55% of Earth's diameter. You include the inner core and the outer core. So the moon's core is very much not like Earth's. It's much smaller. And so the question at the time, is the Earth typical or is the moon typical? You know, the moon is more typical than the Earth is. It's kind of weird. Mercury and Earth have very big cores. Venus, Mars, and the moon do not. And so you look at these terrestrial bodies in the inner solar system. But the other thing, and I'm hoping this little artifact here works. The other thing they found is that two things. The moon wasn't round, and the moon's core is off center. Now, this little diagram here has radically distorted things, but what we found is that two things. With the Earth being down in this direction,
Okay.
that the moon actually had a bulge that hung down toward the Earth, and that was about 20-kilometer bulge toward the Earth. The other thing is the moon's core is shifted about 40 to 60 kilometers, depends on who you talk to, closer to the Earth than not. And so you get this idea, the moon is lopsided. The moon is lopsided. So the other interesting thing, and I've made a little model here to show some of the things that we've found. And this is, again, a model of the moon, and we'll think of the Earth as being down here. And it's interesting, when we talk about down, what are we talking about? The direction toward the center of the nearest gravity well.
Okay.
So when we look at this, and I'm going to use a sophisticated pointer, when we take a look at this, we find, and I made this out of, yes, this is one of my models, made this out of clay. Here's our core, and here's the moon's mantle. And the other thing you notice is that down here toward the Earth, the crust is thin. And up here on the far side, remember this is the near side, far side, right? This isn't top and bottom, but near and far side. The far side crust is quite a bit thicker than the near side crust. And we got that from seismic data too. And so you start pulling these things together. And so not quite out of the blue, but at this point, we see a revival with the three major theories were all knocked out pretty much by, they didn't have to have the whole Apollo program. Apollo 11 KO'd the three major theories. Fission theory, no. Co-formation theory, no. Capture theory, no. None of these made sense according to Apollo data. So now we go back to this other interesting theory. And this theory didn't actually have a real solid development until about 1985, which is quite a ways after, the Apollo era stuff. It's at least 15 years after Apollo. So what's going on? I'll ask the audience to keep in mind that prior to Apollo, most scientists did not believe that meteors could create craters on the Earth. It was, God bless him, Eugene Shoemaker, right? A giant of our science, who was supposed to be an Apollo astronaut, had health irregularities, couldn't go. He was the geologist who went to Winslow, Arizona. He hiked down into Barringer Crater. He did the geology studies. He found shocked quartz grains. He found folded rock. He found all these evidences that said, here is an impact crater. His paper proving comes out in 1966, 67, somewhere in that era. And there was a lot of skepticism. Gene, you're just wrong. Sorry. No. It took a while for people to accept the idea of any impactor making a mark on the Earth. Now we know of about 120 some or a couple hundred impact craters on the surface of the Earth, most of them found from space. We also had the theory from Alvarez and Alvarez, father and son team, in the mid-'80s that, it was a big meteor impact that wiped out the dinosaurs, created an extinction level event. This is pre all of that. So many people at this time dispute meteorites really come from outer space, really? That was something people
that idea that they didn't, I mean, it lasted a long time, there were ideas that somehow lightning created things.
Meteors were lightning shocked metals and minerals. Yes, obviously. Yeah. So there are prior evidences of what we call the big impact theory, but the first one that was brought up academically in a serious form that I could find 1946, a guy named Reginald Daly from Harvard University, and everybody said, Reggie, you're a nut, you're a crank. Nobody believed it, no one accepted it. 67, Shoemaker comes along and says Barringer crater is an impactor. It's not until 1975, and this is 3 years after the last Apollo mission, that a couple of guys named William Hartman and Donald Davis published a paper, and they said, no, the impact theory can work. And what's the impact theory say? And once again here, we're going to put up a diagram and share it with us, with our audience. So there you can see a number of big impact theory diagrams on the web. This one comes from our friends at Wikipedia. And basically the impactor is about the size of Mars. In other words, half the size of Earth. Today we give this planet, which isn't there anymore, the name Thea. And I'm sure that has wonderful mythological connection, but I don't know. It's just Thea. Thea hit the Earth, and there was a glancing impact. It wasn't a bullseye. It was an off-center impact, which, if you think about it, the odds of a dead center impact are kind of small anyway. But this impact off-center basically, it does a couple of things. It basically takes about 10% of the crust of proto-Earth and Thea and just blasts them into outer space. Undoubtedly, there are Thea impact meteorites on the moon and on Mars. Undoubtedly, they are there waiting for us to discover them. And so Mars would be particularly a good place to hunt for them. So would the moon, because they're both geologically dead places. But Mars, because the color of the ground is different from the color of meteorites. Meteorites stand out on the Martian surface. So this impact, about 10% of the crustal material, forms a rocky ring around Earth that's just outside the Roche limit. This rocky ring of debris, if you think about it, what's the materials that's likely to get enough energy to blast into orbit? It's the lower mass rocks, right? The lighter crustal materials. The heavy materials, the core metals, merged. Oh, hello, Earth has a really big core. That's because it's like a double yolk egg, right? There's two cores in one.
Okay.
That old mint ad, two mints in one. Well, Earth has two cores in one. So there's this rocky ring of debris. The ring of debris being outside the Roche limit is not because Earth's Roche limit is really close. It's a relatively lightweight planet. This ring begins to coalesce. It's self-gravity. It starts to assemble into a moon. Simulations indicate this could have been within just 1 to 3 millennia. We had a moon. And we may have had one big satellite. There is a theory that we had one big satellite and a bunch of smaller, minor ones, which could have re-impacted the moons, creating the major Maria. So that's an interesting idea. But eventually this debris coalesces and you get the moon. And as soon as you get the moon forming up, a number of things begin to happen. This diagram, and I'm going to go ahead and stop the share. People will get to see this in a little bigger framework. This diagram gives you evidence of an object which formed in a large gravitational field. Earth's gravitational field pulls the core off center. Earth's gravitational field pulls the mantle off center. Inertia, which creates the tides on the opposite sides of the Earth, creates a thicker crust on the far side. And interestingly enough, when we turn this model around, we see, oh, on the near side, oh, look, lots of Maria. And on the far side where the crust is thick, almost no Maria. The moon, exploration of the moon, one of the most stunning things. And again, people said, oh, it's not real, it's propaganda. The Soviets flew the Lunik probe
Yeah.
around to the far side of the moon about 1966, I think, if that's right, 66 or 7. And they sent back these pictures, and they're very grainy. Today we would consider the whole picture something like about a 70 by 100 GIF, right? It's very low resolution. And they showed that the far side of the moon had 4 tiny Maria. Really, on the near side, they would only be considered lava-filled craters. And they named them the Moscow Sea, the Sea of Ingenuity. They had, surprise Soviet-centric names for them. And it's their right. They discovered them. Hooray. And so then the question is, well, why is the far side of the moon so different from the near side? I mean, if you took Earth and you take a globe and you twist it around, you find continental masses and oceans on all sides, and you find a pole on each ice cap on each pole, and the Earth seems relatively symmetrical. Why in the world would the moon be asymmetrical? And so people who originally saw this data said, oh, well, the probe probably crashed, and these are just fake photos. Do you remember seeing anything like that?
I don't, but
I do. I do remember.
Yeah,
I do remember
propaganda
people
being what it is,
talking heads at the time, height of the Cold War. Oh, well, these aren't real photos, and they've never gotten to the moon before us. The Soviets, the communists couldn't get to the moon before the forces of democracy and light, and so these are fake. How could? And we know because the far side shows only a couple little Maria, and the near side is full of them. Well, it turns out. Wrong again, propaganda spin masters. Photos were genuine. And the far side of the moon, the fact that it's free of Maria gives us evidence that, in fact, the moon was formed here. The moon is a local product. If it had a label on it, it would probably say made in local Earth space because it was formed here. Our gravitation put its physical stamp on the moon. The other interesting thing about the bulge that hangs downward and the off-center core is they created an off-center moon, and the moon was very quickly what we call tidally locked to the Earth. One of the things that's fun to teach to students, and they have a great deal of difficulty with it, is why do we see one side of the moon all the time? And I would do this sort of a discovery thing and say, here's 100 different pictures that I found on the web of the moon in various phases and whatnot, and arrange them all so they're all facing the same way. And after they do that, and oh, look, okay, we've got them so that north is north, south is south, things on the east, things on the west, etc. And I go, okay, where's the pictures of the backside, and why don't we have any? The moon doesn't rotate. Well, sure it does. If it didn't rotate, you would quickly see all of it. And so we get this idea that, yes, the moon does orbit, but if this is our Earth, and we have this idea that, yes, as the moon orbits, one side is always facing the Earth, the other side is not. The moon has a side that's day and night, of course, but more important geographically, it has a near side and a far side, and you can't see the far side unless you fly there and take a photo. The far side is forever invisible to those of us who cannot leave Earth's gravity well. It's never visible to us. Now, the Earth spins quite rapidly. The Earth spins in 24 hours, where the moon both rotates and revolves in about 28 days. So that one side faces the moon. That little video you had in the beginning, Scott, quite nicely showed that the moon wobbles. It has libration.
Right. So you can see a little bit more of the moon than
one activity that I do with students, and we might show how to do this. I call this Lopsided Moon, and I take one of my favorite props, a rubber T-ball. And what we do is we take an X-Acto knife, we cut a cavity in the bottom, and we put in a lead fishing weight, and then fill the hole with hot glue and press it so it's round. and then we make a dot on the other side, roll it around on the floor. Surprise, it always comes to land heavy side down. It's like you can buy trick golf balls with off-center weights so they don't fly straight.
Yeah.
And people make trick baseballs so you can throw a tricky pitch and nobody will be able to hit it because it's lopsided. And if I can't really, I don't have enough room to do this, but when I throw it and spin it, it does indeed wobble because it has a big lead weight that's off center. Well, surprise, you roll this around and it always comes heavy side down. And I point out to students, yeah, heavy side down means heavy side pointed towards the center of the earth. And the moon, heavy side down means that when we look at it, that the near side with all the Maria is the heavy side.
Right.
And yes, it's down, right? It points down into the Earth's gravity well. And so we see the lopsided moon, heavy side down, thick crust on the far side, thin crust on the near side, Maria on the near side, almost none on the far side. The moon matches the Earth's crust. It's younger. We see all these things, and they tend to indicate the moon was made here. And the only mechanism we can come up with is big impact. Well, still big impact. And the big impact theory is essentially it's of an era within about, I think, a year. It came out really seriously within about a year of the giant meteor kills the dinosaurs theory. So the big impact destroyed the dinosaurs and the big impact formed the moon. Those two theories are basically, they came out within the same year. And so you look at this and you see, oh, well, this explains a lot of things. And what's interesting about big impact, it's kind of like Copernicus's sun-centered theory. The Earth is a planet. It's not special. It goes around beyond us are other stars, probably with other solar systems, many worlds. Copernicus makes a simple change. And his simple change, let's move the sun into the center, explains so many things. It explains retrograde motion. It explains seasons. It explains just lots and lots and lots of data fall into line naturally, and we no longer have to struggle or create special circumstances to explain these different things. Well, the big impact theory not only explains the moon's origins, it explains the near side, far side paradox, why the two sides look different, why is the crust on each side different thicknesses, why is the core off center, why are there more Marias on one side than the other? It explains all these things at a stroke. We've talked about Occam's razor before, Scott, the idea that the simplest theory is almost always true. The big impact theory gained acceptance because it suddenly explained so many things that other theories struggled to explain. And we don't have to come up with special circumstances or special anything, special mechanisms or one-off, or this was rare, but it just happened. No, it's all natural. And as we move out into the solar system, we start to see other evidences. Mercury has a very thin crust and a gigantic core. Why? Well, if you had a big impact on Mercury that merged cores and blasted crust material off into space, guess what? The sun's gravitational field is enormous, and it likely, those particles, those crustal materials would have fallen into the sun rather than forming a moon in orbit around Mercury. Mercury is too small. It has this gigantic metal core. We look at Venus. Venus spins backwards. If you look at angular momentum studies, that indicates if the dust cloud is spinning this way, that all planets share that direction of orbit and rotational motion. They're all what we call prograde in the same direction. And yet Mercury spins backwards. How did that occur? Because just from formation, it can't, but several big impacts. The best simulations now indicate Venus had 3 to 4 large impacts. These large impacts would have also released volatiles from the crust and increased the volcanism on Venus many times. Why is Venus's atmosphere so thick? Why does Venus have a runaway greenhouse effect? No, it wasn't SUVs and diesel engines. It was many big planetary scale impacts. We went to Mars and we started to put probes in orbit around Mars and measure the geography of Mars. Gee, surprise, the northern hemisphere averages 10 kilometers lower than the southern hemisphere. There are places where you come to the equator and you've got to climb vertically 10 kilometers to get onto the highland plains of the south. Well, how did that happen? Big impact would do it. Uranos, and yes, I use the Greek pronunciation because we've heard all the jokes. Uranos, its orbit is tilted 98 degrees. All right, it actually orbits sideways. It rotates sideways. Well, you think about that. What could do that to an ice giant planet? Big impacts could do that. And we get into the outer solar system. Pluto, Charon.
Right.
If the Earth could not capture the moon at 1% of its mass, Pluto, even smaller, 0.002 Earth masses, could never capture a Charon, which is 60% of its size and about a third of its mass. Could never happen. But a big impact could split it, and Pluto gravitation isn't enough. And so, gee, Pluto, Charon, a binary planet, their common point, their barycenter, their common point of rotation is out in space between them. And they have, the Pluto Charon has a bunch of minor moons, Nix, Hydra, and a few others. Gee, this is a big impact scenario, absolutely. So as we've explored, we've seen more and more evidence that impacts happen. Big impacts are bad. And there was announced that we see there's a new comet coming in from the Kuiper Belt. And it's coming into the inner solar system, and it's very big, about 150 kilometers wide. Bigger than anything we've seen before. It's a giant. And that's falling in. Big impacts happen. We hope it doesn't happen to us. If we take anything away from this lovely, fascinating story of the origin of the moon, no scientific theory is ever settled, Scott.
Right.
Science is never done.
Right.
And polls don't matter.
Opinions don't matter.
Opinions don't matter. Faith doesn't matter.
Nope.
A theory that lines up with your political, philosophical, or religious beliefs doesn't matter. Data matters. And we must twist theories to reflect facts. We cannot distort or cherry pick facts
Right.
to fit theories. That's a capital error, as Sherlock Holmes said to Watson. And this is truly one of the great triumphs of the Apollo era science. And it's sad. It's virtually unknown. And yet we have this trio of theories, and along comes Apollo and uses the moon like a bowling ball and knocks them all down. And a brand new theory emerges, and it unifies and explains so much that we have learned about other planets and how planets form, the accretion theory of planetary formation. It explains so much, and yet it's not heralded. I would say more people know Benjamin Franklin put a kite up in a lightning storm than know about the big impact theory of the moon. And yet, how much more significant is this origin theory? And I would say more people know the origin stories of Spider-Man, Batman, and Superman than know the origin story of our own moon. It's kind of sad, but we left this to the end on purpose because you never pick up the first comic book and get the origin story right away. It always comes in, the backstory always comes in later.
The prequel.
Right, the prequel. After the series becomes popular, only after Spider-Man is popular do we learn about the radioactive
Oh,
Spider-Man.
you really get that's right.
Exactly. So
Right. Well, we kind of had the same thing. The moon got popular for a long time,
it did.
right? So
It did.
we have some questions here
Hey.
and some thoughts here. Pekka Hautala his question was, and this it's digressing a bit, but it says, does the weight of the Earth change much? Stuff comes from space in tons, but how does the same amount, does it disappear anywhere?
Some people estimate something like 10 million tons of material fall onto the Earth every year, and that's 1 to the 7th kilograms. But the Earth itself is 1 to the 26th kilograms. And so the difference between 10 to the 7th and 10 to the 26th is millions of billions of trillions. It's just no significant. Does the Earth gain weight? Yes, like most of us, from one too many candy bars and bowls of ice cream for 4th of July and one too few laps around the swimming pool. Yes, the Earth does gain mass over time, but it's not even measurable. If it was gaining measurable mass, we would see the effect in the orbit of the moon and our satellites in space, and we don't see it. We can't measure it.
We were talking about computing power at one point, and Book Davies says his phone has more storage than all the Apollo rockets together.
Oh, certainly.
Right?
You realize they sent slide rules to the moon. I have in my collection, I have a Picket slide rule with a box that said Picket slide rules flown by NASA to the moon, because they didn't trust the digital computer. And you can see, I think
they didn't
Apollo 13
require any power to run them.
Yes, they're
Right?
manpower. My 1963 Picket N3 still works fine, thank you very much. I have no calculator older than about 5 or 6 years that's still functional. So my slide rules rock. I love them. I'm a nerd. I have a collection of slide rules, and I think I have my Picket N3 box up here. See if I can find it.
While he's looking for that, Mike Wiesner had mentioned that he had started with, we talked about computers and some of the early internet type of connections or digital connections. Mike Wiesner said he started with a 300 baud modem on his Apple II plus computer.
Yeah,
and that he also wrote programs. There it is.
This is one of the Picket slide rules. And
look at that atomic symbol on there. It's very much like the symbol for your show.
Symbol. And for those of you that don't know, this was $1.95 back in the day. And it has a, there you go.
There it is.
It's a slide rule, and it has logarithmic scales and a cursor. And yes, you can do multiplication, division, trig, logarithms, powers, exponents. You can do everything on this that you can do on a modern scientific calculator. And this one, new in the box, is goodness. And it still has the slide rule guarantee from John W. Pickett. And yeah, this is the world's finest slide rule. And it still works.
This might hark back, this comment from Harold Locke might hark back to the very beginning of our program. He says when he was traveling after high school and visiting the Smithsonian, that they had moon rocks on display, you know, and the plaque in front of it claimed that when we return to the moon, that we would be able to solve all of our energy needs by mining the moon. Is that still true?
Yes, that's very probable. The moon is rich in an isotope called helium-3. And if you look at the chain reaction of fusion, helium-3, you add one more proton and you get fusion reaction to produce helium-4. And essentially, helium-3 is a solar wind product. It does not exist except in a manufactured state on Earth. We can make it artificially. But the moon, solar wind constantly bombards the moon and deposits helium-3. Helium-3 as a fusion fuel, a tanker truck full would supply the energy needs of the United States for a significant period of months. And so it would be an economically viable product. We don't have enough helium-3 here to actually do the research to build a functional reactor. And so, yes, there's a lovely movie just entitled Moon, released by Sony Pictures in the early 2000s. And it was a science fiction about a man who's there by himself, manning a helium-3 mining station.
Oh.
And I highly recommend it if you like thriller sci-fi. It's wonderful. I don't remember the name of the star. He was not a well-known fellow, but yes, that is a viable industry.
And let's see.
Oh, helium-3 will power the moon base. Well, we have to figure out how to make a viable fusion reactor. And I'll remind you that fusion reactors are cusp technology and have been for 40 years.
Yeah.
No one yet has a fusion reactor that reliably produces more energy than you put into it to make the fusion reaction go. So research is needed, but certainly at some point, if you had fusion power, everyone could have an electric car because fusion energy on the Earth is effectively limitless because you can split hydrogen off from water and the seas cover 7/10 of the Earth. So plus what you could mine on the moon. And the resource would be renewable. If you mine the helium-3 on a section of the moon's surface, the sun is going to replace it. Nobody's done the research to see how fast that resource recovers, but certainly the moon is a big place and it would be virtually all mineable.
Great. Let's see. Like Uranus getting tipped on its side, the poles on its sides. Okay.
That's Uranus has the 90.
I seem to remember Alan Stern talking on our program about Pluto and Charon, and that they are both geologically different, though. Geologically different.
I don't think we know that. We haven't got samples. We've looked and seen.
No, right.
We've seen this spectrographically. The very surface regolith looks different, but I don't find that quite overwhelming evidence. But yes, they are tidally locked to one another. Unlike the Earth, which is not tidally locked to the moon is tidally locked to us. The moon has a near side and far side. From the moon, you would be able to see the Earth spinning quite nicely. You would see all sides of the Earth.
And Pekka talks about seeing a documentary about moonquakes or moon shakes. Is the moon far from being a dead body, or is it still?
No, the moon is considered geologically dead for all intents and purposes. The fact that it has an elliptical orbit and it has mostly tidal forces, like we talked about the Roche effect, there's tidal forces that stretch and relax the moon and create quakes. There are lunar transient events that this again cusp science where there's not enough data, but there are people who contend that occasionally moonquakes release volatiles and gases and materials. But there's no indication of active volcanism on the moon in the last 3 billion years.
That's a while.
That's a long time.
Yeah.
And if you do the thermodynamic studies and you say, okay, here's a body of the moon and it starts all at molten temperature, it's had plenty of time to cool off and solidify.
Yes.
And it doesn't have enough, because it lacks heavy metals, it also lacks radioactives, which help power the Earth's geological processes. You realize the Earth is a nuclear reactor and it's captured nuclear energy inside the interior of the Earth that helps keep it molten. Otherwise, it would have solidified by now. Mars, farther away from Earth, the density problem, fewer very heavy metals, probably much less radioactive material on Mars than on Earth. And so Mars is also smaller. Small things radiate heat faster than big things.
Right.
That's why polar animals tend to be big and have fat layers, right? And hummingbirds don't. So we get this situation where, we see that the moon is not geologically active to any significant extent anymore.
As far as
Mars,
lava goes, but there could be like some other types of vibrations or quakes.
oh yeah,
caused.
the idea that simply the libration and the moving in and out
Yeah.
from apogee to perigee puts stresses on the
Tidal
crust.
forces. Okay.
Causes quakes and settling. So yeah, I don't know what the biggest quakes on the moon registered has ever been, but I imagine a Richter or modern scale bigger than 1. I doubt there's been anything. You need very sensitive equipment to detect them. So no major seismic activity.
Okay. All right. Pekka is mentioning that there were the seismological instruments left by Apollo have measured up to Richter 6. So that would be something
Really?
to check out a little
Yeah,
closer.
I want to see that. I wouldn't think the Earth would be or the moon would be capable of producing a Richter 6 quake.
That's pretty.
I've been in a couple of those.
Yeah, that's right.
Yeah, I've been in 3 of 7 point and bigger, and those aren't fun. Yeah,
Wow.
yeah. I
Okay.
was in 3, and no, I didn't want to stay in California for number 4. I'm just no.
Well, we've had them here because of.
We have. I experienced
the,
the Richter 5.5 here, which is in 2015.
Right. I was
And
not knocked out of bed, but shaken awake for that
yeah,
one.
shaken
We're
away.
in Arkansas. Yeah.
Yeah. Biggest quake I was in California. Furniture was bouncing around, cracks were running up the walls, and it was a bad day.
Yes, that's right. Well, there's a question too about the Thea theory is that would there be remnants on the moon and Earth from the Thea event?
Certainly there would be remnants on the moon, on Mars. Well, on the moon is all Thea event remnants. So
it is a Thea event.
It is a Thea remnant, but certainly Mars and Mercury would have Thea impact materials. I have in my collection, Scott, I have meteorites of both Martian and lunar origin.
Mm-hmm.
And so I have rocks in my office here that came from Mars. Yeah. Big impact, big enough to eject them off planet and into space, and eventually fell down the gravity well. And the same thing with the moon. And can't trace them to any impact site. We'd have to go there and do a lot of testing to do that.
A lot of work, yeah.
A lot of work to track that down, but I mean, it's possible that you might be able to someday take a lunar feldspar meteorite and trace it geologically to a particular impact, which would be awesome, but we aren't there in force to do the geology yet. Mm-hmm. We don't have boots on the ground, so.
Not yet. So, and then lastly, we talked a little bit about fusion. I'm posting an article you can read about a prototype reactor with the acronym ITER, and that is the Joint European Torus. Pretty interesting project, but again, this is not a power producing fusion reactor. It's just
experimental.
But it's the next baby steps,
right.
To get there. But they're building it, so and fueling it up. So we'll see how it works out.
And remind everybody, If you know a teacher who's doing STEM this summer, hook them up with How Do You Know? Hook them up with the Astronomy for Educators book.
Right.
Friends, if you haven't downloaded it, go to any search engine, put in Astronomy for Educators, Daniel Barth, it'll pop up for you. The link is there on the website at the end of all the videos. We really appreciate the support of this audience and our fans and friends here. Tell your friends about How Do You Know? Let's make it grow, and make sure you subscribe to the Explore Alliance on YouTube. And for those of you that are interested in teaching, there's an Astronomy for Educators YouTube channel as well. So I encourage you to check that out and subscribe. Follow these things, share them. I guarantee you, if you have a teacher of your acquaintance, a teacher, one of your children's teacher, and you share How Do You Know and Astronomy for Educators and Explore Alliance with them, they will be forever grateful, because it's one of the things more and more teachers are asked to teach, and almost universally they have little or no training in astronomy and space science. So they need this support. The kind of stuff we're doing here that Scott is sponsoring with the Explore Alliance is fundamental science that's improving. It's not only, I'm hoping it's enjoyable for you, and I know a lot of people are here week to week, but it is a fundamental resource for teachers in communities all over the globe. And I'm hoping that you will share this resource and let people know.
Yep. So we will post that right now so that they can go directly to that page and download that link.
There you go. And next week, we're going to go back to our activity type roots, and we're going to talk about how do you know the moon actually goes around the Earth. So we're going to talk about some fun activities that you can do in your backyard. They're great for summertime because the moon is easily visible and the nights are warm, and you can do some fun activities with the moon and your smartphone. And we're going to see about, can we actually track the motion of the moon? Yes, we can. And we'll see how next week on How Do You Know?
Great. Awesome. Okay. And also tomorrow coming up, we have the Open Go-To community, which will be technically episode 160. Jerry Hubble was a little under the weather for last week's Open Go-To community, but he will be. He has a great topic that we'll be sharing with you. And tomorrow night is the 53rd Global Star Party, and our special guest host is the Nebraska Star Party.
Awesome.
People. So they're going to have a live event that will have, an in-person event that will happen August 1st through 6th. But they wanted to share some of the excitement that people have experienced at that particular event, and why you should consider going next time. So because I think it's almost already filled. So until that time, you guys keep looking up. Thanks for all your questions. Thanks for sharing some of your afternoon with us. And we'll be back tomorrow. Take care.
Bye-bye, everybody.
Bye-bye. Hello, everybody. This is Scott Roberts from Explore Scientific. And today I want to talk about the world-famous Galileo Telescope Kit. This is a kit that you assemble by yourself. You'll learn how optics work by assembling the objective lens and also the eyepiece. And there's two different eyepieces that are in this. It's a 25 power, 20 millimeter eyepiece, but it also comes with this very clever little device here that works both as a Barlow lens that will double the magnification of this eyepiece, making it 50 power, or it can be used also as a Galilean eyepiece, which gives 17 power to the telescope. This is what Galileo virtually saw through his own telescope. So you can have that same experience that Galileo had looking at the moon, looking at Saturn's rings, looking at Jupiter. It is a telescope that was designed for the International Year of Astronomy in 2009. And it's a fantastic kit, both for child and adult, to learn how a telescope works. And so if you get the telescope like this, you can either have it on a stand like this, you can hand hold it like a pirate's glass, or on the bottom here, we have a threaded hole here that you could put it on a camera tripod. Very versatile, very rugged, and a lot of fun, all from Explore Scientific.